Hello everyone, welcome to Probability and Statistics for Data Science. As discussed in previous videos, the mean of a random variable represents its average and is therefore, in a sense, a typical value that the random variable takes. This is very useful, but it's also a bit of an incomplete description of the behavior of the random variable. We're often interested also in how much the random variable deviates on average from its average, from its mean. And this is captured by the variance of the random variable. In order to define the variance, we're also going to have to think about how to quantify the magnitude of a random variable, in this case, the fluctuations of the random variable from its mean. And we're going to see that the mean square is a reasonable way to quantify the magnitude of a random variable. Let's get to it. So we're going to talk about the variance, the standard deviation, which as we will see is very related to the variance, and the mean square. In order to motivate why we want to talk about the variance, let's start by reminding ourselves about the mean. So the mean of a random variable, of a discrete random variable, is this weighted sum here, where we weight every possible value of the random variable times its probability. It's designed so that it represents the average value of the random variable if we sample the random variable many times. Similarly, and with the same motivation, the mean of a continuous random variable is the integral of all of its possible values weighted by its probability density. When we compute, when we approximate the mean from data, what we do is we average the data points that we have. So here we have a data set. The sample mean is the sum of all the data points divided by the number of data. We already took a look at this example in previous videos where we showed that the mean provides a very concise description of the behavior of random variables. So here we have temperatures in 134 weather stations in the US. Looking at the individual distributions would take a long time. However, we can just plot all the means and immediately get an idea of how these random variables behave. We immediately see that it's cold in the north, it's hot in the south, and the weather is milder towards the coasts. Okay, we also see immediately here that this weather station in Hawaii, the one with a small circle. So, I should have said this, like the circles are, the radius of the circles are proportional to the mean temperature at that location. We see a very small circle here. This is Hawaii. And that's because one of the weather stations is on a very tall, like on Mauna Loa, on a very tall mountain. All right, so we get a very quick description of all of these random variables, but it's also an incomplete description. What do I mean by that? We're going to take a look at the distribution of temperatures in 3 locations that have approximately the same mean. This is the distribution of temperatures in Bodega, California. The average temperature is around 13 degrees, and we see that the temperatures are very concentrated around 13 degrees. Okay, it's rare that it's much hotter or much colder. This is the distribution of temperatures in Corvallis, Oregon, where essentially the mean temperature, the average temperature is essentially the same. Here we see that it's significantly more common for it to be much warmer and also colder, right, than in Bodega, even though the mean is the same. And now this is the temperature in Missouri, where the average is exactly the same as in Bodega, California. And we see that it's actually very common for it to be either very hot or very cold. So there's much more variation around the mean temperature in Missouri than in California. So how can we quantify this? The challenge here is to quantify the magnitude of the deviation of a random variable from its mean. But how do we compute the magnitude of a random variable, of an uncertain quantity? In order to do this, we go back to thinking about how we actually compute the magnitude of other objects, like for example, numbers. And what's the magnitude of a real number? It's the absolute value, which is essentially taking the square and then a square root. How about the magnitude or the length of a vector in a Euclidean space? Well, typically what we do is we sum the squares of the entries of the vector. Why do we sum the squares? So that there are no cancellations. if one of the entries is very negative and the other one is very positive, we don't want them to cancel each other because we want to quantify the magnitude of the vector. So then we take squares and then we take a square root. And maybe you see where this is going. If we want the magnitude or energy of a random variable, and we know that it can take very large positive values and very large negative values, we don't want them to cancel out. So what should we do? Well, maybe we should take the average of the squared values of the random variable. That's going to tell us how large the random variable becomes, even if there's very positive and very negative values. And that's called the mean square or second moment of a random variable. Let's take a small deviation here to talk about what we use the mean square for, and we will come back to our question of how do we quantify variation in a random variable. The mean square is often used to quantify how well a random variable approximates another random variable, and that is called the mean squared error. So here, one of the random variables, we're going to call it E because it's an estimator, and the other random variable is A, which is what we want to estimate. So if we're wondering how well we are doing estimating an uncertain quantity using another uncertain quantity, this is a very reasonable, a reasonable way to quantify that, to quantify the error. To illustrate a possible use of the mean squared error, we're going to derive what is the best constant estimate of a random variable. So you have some random variable and you want to estimate it, but you can only use a single number, okay? You would sample the random variable many times and get different values, but you're always going to estimate it using only a single number. What should that number be? So what we do here is we're going to minimize the mean squared error with respect to that constant estimate. This is the mean squared error. We're going to expand it, and we apply linearity of expectation. So the mean squared error at the end of the day, if we apply linearity of expectation, this constant C can come out, and we end up with the mean and the mean square of the random variable, an expression that depends on that. Now we would like to minimize the mean squared error with respect to C. So what do? We just take derivatives. It's really easy to take derivatives. Remember, these are derivatives with respect to C because that's the parameter that we want to set. The first derivative is 2C, 2 times C minus the mean, right? I mean, the derivative of this is 2C, the derivative is 2 times the mean. The second derivative is just equal to 2. So this means that the function looks like this with respect to C, where this is the MSE as a function of C. And to find the minimum, we can just set the derivative to 0. And the minimum is at the mean of the random variable. This is kind of nice because it gives you another motivation of why the mean in a way is a typical value of for the random variable. It's basically the best constant estimator of the random variable. If you only know, if the only thing you know about the random variable is its distribution, and you have to estimate it using a single number, in terms of mean squared error, that single number should be the mean. Okay, but let's go back to why we were talking about the mean square to begin with. It's because we wanted to quantify the fluctuations of a random variable around its mean. So what are we going to do? We're going to compute the mean square of those fluctuations. So this is the random variable, this is its mean, and now we compute the mean square of those fluctuations, and this tells us how much the random variable is varying around its mean. That is the variance. Usually we don't compute variances in this way. We're going to see this a little bit later on when we derive the variance of different parametric distributions. What we do is we expand this, this expression in the following way. And this is actually good practice because you have to get used to differentiating between random variables and constants that are obtained, for example, by computing the mean of a random variable. So in this expression here that we have inside the mean, once we have expanded things, let's identify what is a random variable and what is a constant. So in red, I'm going to tell you what is a random variable. This guy is a random variable. This guy is a random variable, and I'm done. Why? Because the mean operator, with this guy here and this guy here, maps the random variable to a constant. So once we have applied the mean operator, that's already a constant. We treat it like a constant. So now when we apply linearity of expectation here, we're going to have that this is equal to the mean of this term minus the mean of this term. But when we compute the mean of that term, we treat this guy as a constant. So it can come out of the expectation, and we're left with 2 times that constant times the expectation of A. All right? And then this guy is just a constant, so its mean is itself. So now what do we have here? We have the mean square minus 2 times the square of the mean plus the square of the mean. So this is just equal to the mean square minus the square of the mean. And this is usually an expression that is easier to compute. I mean, it depends, right, on the situation, but this expression can often be easier to compute, and we will actually apply it later on. All right, so the variance is the mean square of the deviation, and we can write it as the mean square of the random variable minus the square of the mean. The standard deviation of a random variable, which we often denote with a sigma, is the square root of the variance. Let's compute the variance and the standard deviation for a uniform random variable that is uniform between A and B. We already know the mean from the previous video on the mean of a random variable. So now we will compute the mean square, and we subtract the square of the mean using the identity we derived. So to compute the mean square, we have to integrate u squared, okay, because this is a function. This is like when we're doing the mean of a function, just to be clear. Okay, and in this case, well, this is a weird looking u. The function is u squared, right? So what do? We plug in the function, and then we integrate it against multiplying it by the density. The density here is just equal to 1 over b minus a from a to b. So we get this expression. The antiderivative of u squared is u to the power 3 divided by 3. So we plug that in, and now we cancel out, and we get this expression here for the mean square. But now we have to take this and subtract this guy squared in order to get the variance. Here I recommend that you just do this on your own, writing it down, and verify that everything is fine. But at the end of the day, what you should obtain is that the variance is equal to the mean squared minus the square of the mean, which is equal to b minus a squared divided by 12. So if we take the standard deviation here, the standard deviation of a random variable that is uniformly distributed between a and b is equal to the length of the interval, right? B minus a, the square root of b minus a squared, divided by square root of 12. Okay. If you want to visualize that, here in pink, I have drawn the mean plus the standard deviation minus the standard deviation. So all of these points are within 1 standard deviation of the mean. Okay, so that is what is quantified by the standard deviation of the uniform random variable that we have just derived. What about when we need to approximate the variance from data? We want to quantify how much a quantity varies around its average. Well, what we do is we first compute the average. That makes a lot of sense, right? And then we subtract the average from each of the data points. We square that because we don't want cancellations. And then we divide by the number of points. And you might be wondering, why do we divide by the number of points minus 1? This doesn't matter very much, but it basically gives you an unbiased estimator. We will see later on what the bias of an estimator means. For now, this is not too important. You divide by the number of points. All right? When you have a lot of points, it just makes no difference. So the sample and if you want the sample standard deviation, you take the square root of this sample variance. Okay, so let's go back to our motivating example where these 3 guys had exactly the same average, but their behaviors are clearly very, very different. So maybe think for yourself, where do you expect to see the smallest standard deviation and the largest standard deviation? Well, clearly, this guy has a very small standard deviation. only 2.9, only 3 degrees. So on average, we see deviations of 3 degrees, very, very little. What about in Oregon? We see deviations of 7.5 degrees. So there's more deviation, which corresponds to the shape of the distribution, right? We see that here relatively often it's actually quite warm and it can get quite cold. And then in Missouri, the changes are more extreme, like it can get very hot and it can get very cold. This is also reflected in the standard deviation, which is 10 degrees. So on average, there's 10 degrees deviations from the mean. All right, so here we see that the standard deviation does provide this information that was missing from the mean. This is the map of the means. Now I'm going to show you a map of the standard deviations. Before I show you, maybe you can try to think how they're going to look. Where do you expect more standard deviations? Where do you expect less? And this is how this looks like. So if you know a little bit about climate, continental climate, which is far from the coast, is typically more extreme. So that's why we see much higher standard deviation there. And we see much smaller standard deviations around the coast, where it's, like Florida also, the changes are very mild. We see that the west coast of the US has a much less extreme, has less extreme variations than the east coast. In fact, I used to live here and I much prefer the winters there than here. Interestingly, in Hawaii, we see that even at high altitude, there's not that much variation around the year. Like the temperature, the standard deviation is extremely small. I should have said, maybe you already figured this out, but the radius of each of these circles is proportional to the standard deviation. So again, the standard deviation provides this complementary information that is missing from the means. Now let's take a look at an important property of the variance of a random variable. Let me ask you, if we scale a random variable by a certain constant, like by 2, and we shift it by 3, how do you think the variance of the random variable should change? So let's first reason a little bit by common sense, and then we'll do some math. By common sense, do you think that shifting the random variable is going to make any difference? This is a systematic shift, okay, that happens for every possible sample of the random variable. Well, no, right? Because we're only interested in the variation of the random variable around its mean, so shifting it should make no difference. What about scaling it? Well, if we scale it by 2, the standard deviation should be also scaled by 2. So from that point of view, the variance should be scaled by 4. Let's take a look at and see if this is true. So this one instance where we're going to compute the variance of this new random variable C1a plus C2. Here, I'm going to use the original definition of a random variable. I'm not of the variance of a random variable. I'm not going to do the mean square minus the square of the mean. Okay, you will see why. So here, this is, you can think of this as a random variable b. So if we want to compute its variance, this is b minus the mean of b. All right. And here, as usual, what am I going to apply? Linearity of expectation. So here, C1 is going to come out and C2 also. We get C1 times the mean minus C2. So what happens? As we had predicted, this shift that we apply gets cancelled out, which makes a lot of sense because we're only interested in variations around the mean. And now we see that we end up with this constant C1 that is going to be squared. And once it's squared, it can come out. So we have that this is equal to C1 times the mean of the deviations of A from its mean, the squared deviation of the mean of the squared deviation of A from its mean, which is just the variance. So as we had predicted, the shift doesn't matter at all, and the scaling factor is applied to the variance, but squared because the variance is a squared quantity. All right, so now to end this video, I'm going to show you the variance of different parametric distributions. I'm not going to, go very deeply into the calculations. What I would suggest is like maybe you pause the video before each of them and you try to compute it out, or you just listen to me, about how you would do this. When I used to learn probability, I feel like an old man saying this in my time, but it's true. Like when I was in undergrad and we learned about probability, there was a lot of emphasis on this type of calculations, like compute the variance of I don't know what, which got really complicated. to be honest, I don't think that's super useful. It's important to know how to do it to some extent, but it's much more important to understand why, what the concepts actually mean intuitively and how they're going to be reflected when you actually manipulate data, in my opinion. But still, knowing how you compute these things is not bad. For a Bernoulli, it's really easy, right? So we already saw that the mean of a Bernoulli is theta. What about the mean square? Well, this is going the square of this random variable also has just values 0 or 1 with probability 1 minus theta and theta. So the mean square, okay, 0 or 1. What's this probability? 1 minus theta. What's this probability? Theta. I know that sometimes I say theta, sometimes I say theta. I can't control it. Sorry about that. So this is theta. So now in order to compute the variance, we have to take this guy and subtract the square of the mean. So this is going to be theta minus theta squared, which is equal to theta times 1 minus theta. You might want to plot this as a function of theta, and you will realize that the maximum variance occurs when theta is equal to 0.5, which makes a lot of sense because that's where you get more fluctuations in the value of the Bernoulli random variable. All right, let's take a look at a geometric random variable. We know already the mean from our previous video on the mean of parametric distributions. Let's compute the mean square. How do we do that? Well, we have this function that is the square that we want to compute. We weight it by the PMF and we sum. Now here we get this expression which has this power but also k, so we need some kind of expression derived from the geometric series. We had already derived this in the video of the parametric distributions, basically looking at the geometric series and taking derivatives. What are we going to do? We take derivatives again. Okay, when we take derivatives again, we get this expression in terms of gamma. Here we again do the change of variable gamma equal to 1 minus alpha, so that we have an expression like this here. This alpha is going to go away here. And what do we get? We get a 1 minus gamma cubed that is actually just alpha cubed. But multiplied by this alpha that was coming out, that becomes an alpha squared, and we end up with a 2 minus alpha up here. Again, not super interesting. Take a look on your own. The point is that this comes from the geometric series. Now, once we have the mean square, we subtract the square of the mean to get the variance, and we see that this is the variance of a geometric random variable. So after doing all of these computations, you might be tired of doing computations and you might just end here. This is maybe the most important moment in which you have to say, okay, what does this actually mean? What does this expression mean? What this means is that the standard deviation, the typical deviation from the mean in a geometric random variable, scales like 1 over the value of the parameter. So for example, we have a parameter that is 0.2. These are all the values that are within one standard deviation. And in general, as we decrease the parameter, the standard deviation grows linearly with 1 over the parameter. That's what's important about the expression that we have just derived. What about a Poisson random variable? This looks super scary, but we're going to essentially use the same tricks to compute the mean square that we use to compute the mean. We have this expression for the exponential function, and essentially we just want to plug it in. So first we start by canceling out one of these k's with the factorial, but now we have a problem because we cannot cancel the other one. So we do this trick where we separate this into k minus 1 and 1. Okay, we separate it in this way, and now we can cancel out this guy, so we're happy. So we get two expressions in terms of something like the exponential, one where like lambda squared is going to come out, another one where just lambda is going to come out. Again, do this on your own, but what you're going to get is that at the end of the day, once you cancel out this exponential with this guy, is that the mean square is equal to lambda squared plus lambda. So if I subtract the mean, what do I get? The mean square, sorry, and the mean, remember, is equal to lambda. The mean is equal to lambda, so the square of the mean is equal to lambda squared. So the variance is equal to lambda. In a Poisson, the standard deviation of the random variable grows with the square root of the parameter of the Poisson. All right, that's what's important here. So this standard deviation is going to grow with the square root of the parameter of the Poisson. What about an exponential random variable? Again, let's compute the mean square. These are continuous random variables, so we have to take an integral of the square against the density. We plug in the density of an exponential, and here, as we did for the mean, we're going to apply integration by parts. Okay, where like we separate the two parts. One of them we differentiated, the other one we compute the antiderivative. You know, maybe review it on your own. This part is just going to be 0. Okay, and then here we have something that is actually the mean of the random variable, so that's going to be equal to lambda. And we end up with, what lambda? 1 over lambda, sorry. So that's where this square comes from, 1 over lambda times 1 over lambda. And now we have to subtract the mean from this. And we get a pretty interesting result. We get the result that the variance is equal to 1 over lambda squared, so the standard deviation is equal to 1 over lambda. The standard deviation is exactly equal to the mean. So that means that for an exponential, you get fluctuations that are on the order of the mean, which sounds, like quite strange. But then when you, so this is what the fluctuations look like. And as you can see, the fluctuations are as large as the mean, very large fluctuations. So this begs the question, are we actually going to see this kind of stuff in practice? So let's go to our call center data where we were modeling the inter-arrival times between calls as a parametric distribution that was exponential. What is the sample mean? 30.8 seconds. I believe it's seconds. What is the sample standard deviation? It's even larger. It's 33.6 seconds. So we do see this kind of behavior in real data that, that follows approximately an exponential distribution. And again, more than the actual computations, you have to ask yourself, what does this mean once you have reached the result? And this will also allow you to sanity check your calculations. All right, so we're almost done here. Now, Gaussian random variable, we're going to compute its variance. Remember that a Gaussian random variable has a variance parameter, sigma squared. So hopefully we will find that the variance is equal to that. First, we need to compute the mean square of the Gaussian random variable. We do that by writing the square, weighting it by the density. Here, as usual with Gaussian random variables, we're going to take a change of variable where we're going to say that t is equal to a minus mu divided by sigma. We plug this in, and now we get these two expressions because of this square here, where we get something in terms of t squared and in terms of t. Oh, and also, we have to completely expand the span, so we also have this term here. If you calculate this, which maybe I should do a video where I try to do this from scratch, and then you just laugh at me. So these things are not, necessarily very easy. You get that, you get this expression where you have a mu squared here. Remember that this is going to be equal to 0 because this is a function that is, so we're taking the derivative of something that is antisymmetric. So basically this cancels out at infinity and minus infinity. And essentially you get sigma squared plus mu squared, which is great because now when we compute the variance, we have basically sigma, the variance of the random variable is equal to the variance parameter. This is why we called it a variance parameter. Now, if you remember how you approximate this variance parameter, it's essentially the same as computing the sample variance, but if you apply maximum likelihood, you divide by n. You don't divide by n minus 1. And that's part of why I'm saying that it doesn't really matter, this n minus 1, very much, because n is typically going to be quite large. All right? So essentially, when we fit a Gaussian, what we're essentially doing is saying, oh, the mean parameter is the sample mean, and the variance is the sample variance, or something very close to the sample variance. So when we this would be the method of moments. If you do maximum likelihood, you get essentially the same approach. Here is a Gaussian with standard deviation 1, and this is what, these are the values that are within 1 standard deviation of the mean. Okay, so what have we learned? We have learned the definition of variance, which was motivated by the fact that the description of a random variable in terms of its mean is kind of incomplete because it doesn't tell you the fluctuations around the mean. This motivated us to derive some way of quantifying the magnitude of a random variable in order to quantify the magnitude of the variations around the mean. We came up with the mean square, and on the way we showed that the mean is the best constant estimator for a random variable in terms of mean squared error. And then we used that to define the mean and the standard deviation and explained how to approximate them from data. And then we derived the variance of some popular parametric models. And that's all I got. Thank you very much.